Okay, here now I'm going to introduce the standard deviation, the variance and the standard deviation, the important measures. And to start, you have to understand that we are measuring the distance from the center, right? Center is already calculated, say, the mean is known. We learned how to calculate the mean. And now what's lost in the mean is the information lost in the mean is the distance. It ignores the how far the observations are from the center. So we are going to use that as the to define the measure. So first, the mean. I'm going to denote the mean as simply the expected value of x as the center. So and then deviation of the ith observation. So suppose that there are n number of observations, right? Uh, like say 100, there are 100 observations. And then for each of them, there are 100 observations and there is one center. And then for each observation, so you can measure the distance. So for each observation, there is one distance. So there are 100 distances. We call the distance as the deviation. So deviation is defined as an observation minus the center. So it's the distance. So difference is the deviation. So let's think about a simple data. Of course, it's not real data. Honolulu's, I will take simple four numbers. Honolulu's temperature in a year is distributed like this. Spring is 76 degrees, summer is 82 degrees, fall is 80 degrees, winter is 74 degrees, simply. And if it's just four numbers or four raw data, so you measured the temperature at only four times, and if you calculate the mean, you know how to calculate the mean. So it's simple. Add all the four numbers and divide by four, then you get 78 degrees. That is the mean. Then what is not included in the mean is the differences, right? So subtract 78 from each of the observations. Right? There are four observations. Then 76 minus 78 is minus 2. And 82 minus 78 is plus 4. And 80 minus 78 is plus 2 and minus 4. In that way, these are deviations. So, and the deviations are exactly what we want. It's the distance differences. And also, as I said earlier, there are four observations, and you can define the distance differences, deviations for each observation, right? As you see, there are four deviations. So you may think the deviations as a transformation. So the original data are these four numbers, but after the transformation I just explained, subtracting a number, it's a linear transformation. Subtract this number, then you get another random variable, and we are going to call the random variable as the deviation. So there are still the same number of observations for this new random variable deviation, right? And then what we are going to do for the next step is that what we want is the distance from the center. Then the negative sign does not help. It does not help in our analysis. Therefore, so simply intuitively, plus 4 and minus 4 are equally far from the center, so there is no reason to distinguish them. I don't care about the direction, whether it is positive direction or the negative direction. What we want is the absolute value of the distance. To remove the signs, what we are going to do here is instead of taking the absolute value, we take squares. Square all the deviations. Then we get squared deviations. Mathematically, you can write it this way. So inside is the deviation. Take square. So minus 2 squared equals 4, plus 4 squared equals 16, plus 2 squared equals 4, minus 4 squared equals 16. As you see, minus 2 plus 2 have the same square deviations, and plus 4 minus 4 have the same squared deviations. So you may interpret the squared deviations as the distance from the center. Now it's always positive. The square deviation equals 0 only when the observation equals the mean, right? So square deviation equals 0 only when the deviation is 0. And the greater the deviation, the greater the square deviation is. So it's a natural interpretation to think it as a distance. And then also you may think the square deviation as another new random variable after two transformations. The first transformation is subtracting the mean, and the second transformation is taking a square. So after the two transformations, you obtained another new random variable. And there are 4 observations for the newer random variable. So this new random variable has 4 observations, 4, 16, 4, 16. And then, right, so this is our, after the transformation, we get this observation. And now what we are going to do here is you may calculate its mean. You can calculate the mean of this transformed random variable. The random variable has 4 observations, so you can calculate the mean, and that is the variance. The variance is the mean of the squared deviations, right? So if you are confused, try to uh, try to think it as a transformation and then calculating the mean, because we practiced that in the previous chapter. I I I showed you how to take the mean of a transformation. So same thing happens, right? You can understand this as a special case of transformation of a random variable. And then the larger the variance is, so if you interpret the square deviation as a distance, then the variance can be interpreted as an average distance. But just simply the distance is measured as a square deviation. So the variance is a kind of average distance from the mean. Therefore, the larger the variance is, the more variation in data. So the further away the observations are from the center, from the mean, right? So remember, excuse me, think about this. So the red histogram is more concentrated. That means the distance from the center is on average smaller than the blue. The blue is more spread out, so the average distance from the center is greater for the blue. So exactly the difference is captured by uh, by the variance, and it is always non-negative. It can be zero. It may be zero, but it cannot be negative. It's non-negative. The reason is because we already took squares. So after taking squares, you cannot have a negative number. And it's denoted as sigma squared. It's Greek letter sigma, sigma squared, or alphabet S, S squared. This is the typical notation, right? I have so since the like from the very beginning of the course, I have been emphasizing this distinction. You have to at least imagine the population and the sample, the and in this case, same distinction happens to the variance. The population variance can be thought of as the variance you calculate from an infinite number of observations. Of course, it's not possible, it does not exist in reality, but just theoretically, hypothetically, uh, it exists. On the other hand, the sample variance is calculated from finite number of observations. So this is the typical, the more fundamental distinction between population and sample. However, what I don't like is that these names, population variance and sample variance, those terms are used for different formulas. So there are two different formulas for the variance, and their names are population variance and sample variance. It has nothing to do with these two guys, right? Because so let me explain the formula. So the population variance formula takes this form. So remember, the square is this is square deviation. So you add all square deviations through all the observations and then divide it by the sample size, which is, so this part is taking the average. So take the average of square deviations. So this is how we defined the variance. But this formula is called the population variance. But there is a different formula called the sample variance formula, which is dividing the summation by n minus 1 instead of n. So it's subtracting 1. So actually, the sample variance formula is more commonly used. So I will show you the Excel, Microsoft Excel has two different formulas built in. So let me show you. So these four numbers are what we used as an example in the slide. And let's calculate the variance of these four numbers. Excuse me. Here. Let's think about this formula insert function. If you search for variance, uh, search for, excuse me, variance, there are two formulas. VAR, it's actually obsolete, I think. Uh, it's used in 2007 or earlier. These days, these two are the main formula, Excel formula for variance. var.p is the population formula, and .s is based on a sample. So you have two formulas. I'm going to use them. I'm going to use both of them. So the variance, the population variance is 10, and I am going to use the sample formula. Sample formula has a different number. So they are different. They are different. If you use an older formula, it returns the sample formula. So this is sample variance, and this is population variance. There are two different formulas, and this is older formula used in the earlier versions. And as you can see from this, the default is the sample formula. It's really annoying. And if you apply these two formulas to our example, as you just saw, the only difference is the denominator. The denominator either n or n minus 1. So there are 4 observations. You are calculating their average, and the population variance equals summation divided by 4, which is 10. Sample variance equals summation divided by 4 minus 1, which is 13. So they are different. Uh, I have to teach that because both still the population variance is used. So you need to know both of them, but also you need to know that the sample variance formula is the default. It's more commonly used. And uh, now I cannot explain why we use n minus 1, but I'm going to explain the reason in chapter 8. So wait a few more weeks, then I'm going to explain you. So, okay, I will stop here and I'm going to continue about the variance in the next video. Thank you for watching and continue watching. I'll continue watching soon.